At this very moment, even while your vehicle seems to be performing just fine, there might be a single contaminated sensor quietly draining horsepower, guzzling extra fuel, and accelerating engine wear, all without ever illuminating a single warning indicator on your instrument panel. That's precisely what makes this situation so treacherous. How is it possible that a component barely larger than the tip of your thumb can cause a vehicle to feel lethargic, consume excessive gasoline, and catastrophically fail emissions inspections simultaneously? Automotive repair facilities and dealership service departments throughout America witness this identical scenario repeatedly. Technicians replace spark plugs, swap out ignition coil packs, point fingers at fuel delivery systems, and vehicle owners hemorrhage thousands of dollars in diagnostic fees and unnecessary parts. Yet the underlying issue persists stubbornly until someone finally takes the time to properly clean a sensor that practically nobody ever bothers to service. And here's the kicker. It's not the sensor most automotive enthusiasts immediately think of. There exists a hidden perpetrator that gradually collects contamination over multiple years of operation, transmits erroneous information to your engine control unit, and transforms what should be a perfectly functioning power plant into a persistent disappointment. Throughout the duration of this comprehensive breakdown, we're going to methodically examine the most troublesome engine monitoring sensors individually, analyzing their function and failure modes. However, the single sensor that malfunctions most frequently receives the least maintenance attention and possesses the capability to completely revolutionize your engine's behavior in mere minutes. That revelation will only come at the absolute conclusion of our discussion. But before we dive into these critical sensors, if you want to keep your vehicle running at peak performance and avoid costly repair bills, make sure to subscribe and hit that notification bell. We're constantly sharing professional automotive knowledge that can save you thousands of dollars in unnecessary repairs. Now, let's get started. Number 13. The MAF sensor. Mass airflow measurement. The mass airflow sensor stands as simultaneously one of the most vital yet consistently overlooked elements in contemporary fuel-injected powertrains. Its fundamental responsibility involves measuring with remarkable accuracy every single gram of atmospheric air being drawn into the combustion chambers. The overwhelming majority of MAF sensors installed in vehicles distributed throughout the United States utilize what's known as a hot wire architecture, employing an extraordinarily delicate platinum filament approximately equivalent in diameter to a single strand of human hair. This wire element receives electrical current that maintains it at a predetermined constant temperature, and as incoming air rushes across its surface, the airflow actively cools the heated wire in direct correlation to the velocity of that airstream. What your engine control computer is genuinely monitoring isn't the air itself, but rather the precise amount of electrical amperage required to sustain that wire at its designated stable temperature. This current measurement gets instantaneously converted into comprehensive air mass information, with updates occurring in mere milliseconds. The serious complications begin their development when infinitesimal dust particles, petroleum vapor residue from aftermarket oiled element air filters, or generalized environmental pollutants begin coating that exceptionally fragile sensing wire. Once this contamination layer forms, the thermal characteristics of the wire fundamentally change, and consequently, the data transmitted to your engine's computer becomes increasingly inaccurate and unreliable. The ECU now operates under the false impression that either more or less air is entering the intake manifold than what's actually occurring in reality, and it compensates by commanding delivery of an incorrect quantity of fuel to match this fictional airflow reading. The resulting symptoms frequently prove confusing and difficult to diagnose. Drivers experience pronounced power deficiency during aggressive acceleration attempts, fuel economy mysteriously deteriorating without any obvious mechanical explanation, idle quality becoming unstable with random fluctuations, and in particularly severe contamination cases, complete engine stalling when decelerating to a complete stop. Diagnostic information compiled from automotive repair facilities across the United States reveals that approximately 40% of all vehicles exhibiting rich or lean air fuel mixture diagnostic trouble codes are suffering from contaminated MAF sensors, not actually failed sensor units. Correct cleaning methodology requires utilizing a purpose-formulated MAF sensor, cleaner aerosol product, and maintaining a completely hands-off technique that never physically contacts the delicate sensing element with any solid object. Yet, there exists another air measuring sensor operating on an entirely different technological principle. Number 12. The MAP sensor. Manifold absolute pressure. The manifold absolute pressure sensor represents a fundamentally alternative engineering approach for calculating engine load conditions. This technology appears commonly in speed-density fuel injection architectures found extensively in numerous American manufactured vehicles. Rather than directly measuring the quantity or velocity of airflow, the MAP sensor instead monitors the pressure level existing inside the intake manifold itself. The sensor employs a piezo-resistive element that alters its electrical resistance characteristics in direct response to pressure forces applied against its sensitive surface. In straightforward terms, it functions as a transducer, converting mechanical engine loading into an interpretable electrical signal. During periods when the throttle valve remains closed and the engine operates at idle speed, intake manifold vacuum reaches its maximum levels, and the sensor consequently reports relatively low absolute pressure values, typically falling somewhere between 20 and 30 kilopascals. Conversely, during wide-open throttle acceleration events, vacuum levels plummet dramatically and pressure rises toward atmospheric levels, reaching approximately 100 kilopascals when operating at sea level elevation. The engine control unit synthesizes this pressure data together with current engine rotational speed and intake air temperature measurements to mathematically calculate the actual incoming air mass using sophisticated thermodynamic computational equations. The critical failure mechanism usually doesn't originate from the sensor component itself, but rather from the vacuum supply source feeding it with reference pressure. Deteriorated vacuum hoses exhibiting cracks, loosened connection fittings, or partially detached supply lines permit atmospheric leaks that completely distort the pressure readings being transmitted. The sensor erroneously reports diminished vacuum compared to actual conditions, misleading the ECU into believing the engine experiences heavier loading than reality dictates. The predictable consequence manifests as excessive fuel injection commands, skyrocketing fuel consumption rates, visible black smoke emissions from the exhaust system, and persistent rich air-fuel mixture fault codes stored in computer memory. In authentic real-world diagnostic scenarios performed in professional repair shops, simply cleaning the MAP sensor vacuum port thoroughly and methodically verifying complete hose integrity successfully resolves roughly 80% of problems initially attributed to sensor malfunction. However, an even more influential sensor exists when considering emissions control performance. Number 11. The oxygen sensor. Lambda. Sensor technology. Oxygen sensors strategically positioned within the exhaust system function as your engine computer's primary visual perception for continuously monitoring combustion efficiency in real-time operation. These sensors constantly fine-tune and adjust the air-fuel mixture ratio thousands of times every single minute of engine operation. The vast majority of vehicles operating in the United States incorporate zirconia-type oxygen sensors, which depend upon a specialized ceramic element that must be heated to temperatures exceeding 300 degrees Celsius. This ceramic element generates a measurable voltage output based upon the differential in oxygen concentration existing between exhaust gases passing through the pipe and ambient outside atmospheric air. When an engine achieves combustion at the theoretically ideal stoichiometric ratio of precisely 14.7 parts atmospheric air to 1 part vaporized gasoline, the oxygen sensor produces an output voltage of approximately 0.45 volts. Should the combustion mixture shift toward lean conditions and oxygen content within the exhaust stream increases proportionally, the sensor voltage output drops below the 0.3 volt threshold, electronically signaling the ECU to command additional fuel delivery. With excessively rich mixture conditions, voltage readings climb above the 0.6 volt level. The major deterioration problem materializes when these sensors accumulate contamination from lead compounds, silicone-based materials, or phosphorus deposits, frequently caused by substandard fuel quality or engine oil consumption resulting from worn piston ring sealing or compromised valve stem seals. These chemical contaminants literally poison the zirconia ceramic element at a molecular level, dramatically slowing its response time characteristics and reducing measurement sensitivity. The sensor continues functioning, but in an increasingly sluggish manner, transmitting delayed electrical signals that the ECU struggles to interpret with proper accuracy. The predictable outcome involves slow oscillation patterns between rich and lean mixture commands, accelerated fuel consumption, noticeable power output reduction, and virtually guaranteed failure during mandatory emissions inspection testing procedures. Nevertheless, there remains one position-sensing sensor whose malfunction generates a completely different symptom profile. And that's precisely where this narrative becomes even more compelling. Number 10. The TPS, Throttle Position Sensor. The throttle position sensor functions as a precision-engineered potentiometer mounted directly onto the throttle valve shaft assembly, and its singular responsibility involves communicating to the engine computer exactly how much throttle input the operator is requesting at every conceivable instant. Despite appearing deceptively simple in construction, it represents a critically important component in modern engine management. Contained within the sensor housing exists a circular resistive track element, and a movable electrical contact slides progressively along this track as the throttle valve opens and closes in response to accelerator pedal input. This mechanical movement proportionally divides the reference voltage supply corresponding to throttle angle position, characteristically producing approximately 0.5 volts when the throttle sits at the fully closed position and approaching 5 volts at wide-open throttle conditions. What the engine control unit accomplishes with this positional information proves absolutely critical to proper vehicle operation. The computer determines whether the driver intends gentle acceleration, where fuel economy optimization takes priority, or aggressive acceleration, where the engine requires enriched fuel mixtures combined with advanced ignition timing strategies for maximum power output delivery. The genuine problems initiate when the internal resistive track material begins experiencing wear deterioration or becomes contaminated with debris, creating what technicians call dead spots in the sensor's operational range. Within these affected zones, the voltage signal briefly drops out completely or fluctuates in unpredictable patterns. These dead spot areas almost invariably develop at the most frequently utilized throttle positions, such as steady-state highway cruising speeds or elevated idle positions during stop-and-go traffic conditions. From the driver's perspective behind the steering wheel, this malfunction manifests as jerky acceleration behavior, sudden hesitation events, momentary power loss occurring at very specific accelerator pedal positions, or, in extreme deterioration cases, complete engine shutdown when the throttle passes through those excessively worn regions of the potentiometer track. In professional diagnostic procedures, technicians verify TPS functionality by gradually opening the throttle mechanism while simultaneously monitoring live voltage data streams on a professional-grade diagnostic scan tool, specifically searching for sudden voltage drops or unexpected spikes that clearly indicate internal wear degradation of the potentiometer element. Number 9. The Crankshaft Position Sensor. Without a functioning crankshaft position sensor, a modern electronically controlled engine operates in complete darkness, metaphorically speaking. This compact sensor, mounted in extremely close proximity to either the flywheel assembly or a toothed reluctor wheel attached to the crankshaft, generates precisely timed electrical pulse signals every single time the machine teeth pass directly by its magnetic sensing tip. What's genuinely transpiring is that the ECU utilizes these pulse signals to determine the exact rotational position of every individual piston at all moments during operation, along with the precise rotational velocity at which the entire engine crankshaft assembly is spinning. This positional and speed information provides the fundamental data that allows the computer to determine exactly when fuel injection should occur and precisely when ignition spark should fire for each cylinder. When this sensor becomes contaminated with metallic debris particles, carbonized oil residue deposits, or general accumulated grime, the electrical signal output becomes distorted and intermittent failure events begin manifesting. The engine may shut down unexpectedly when reaching normal operating temperature without providing any advance warning, require extended cranking duration before achieving initial startup, or experience momentary spark interruption for fractions of a second while driving down the road. In automotive repair facilities throughout the United States, it proves extremely common to encounter engines that superficially appear to suffer from serious ignition system failures or fuel pump malfunctions, only to achieve complete recovery after nothing more than cleaning the sensor tip thoroughly, removing accumulated metal shavings with a lint-free cloth, and treating the connector with a specialized electrical contact cleaning solution. However, understanding crankshaft position information alone proves insufficient for optimal engine operation. The computer additionally requires knowing exactly what position the camshaft occupies at any given moment. Number 8. The CMP, Camshaft Position Sensor. The camshaft position sensor operates in perfect coordination with the crankshaft position sensor, like two meticulously synchronized timepieces. While the crankshaft sensor communicates overall engine rotational speed and angular position, the camshaft sensor reveals the exact phase point within the four-stroke engine cycle for each individual cylinder. This capability enables precise sequential fuel injection timing and accurate control over variable valve timing system operation. The sensor typically mounts within the timing chain or belt cover assembly, or directly on the cylinder head casting, where it reads either a trigger wheel or a solitary metal protrusion machined onto the camshaft itself. Its genuine purpose involves sending one unique reference pulse signal per complete camshaft revolution, specifically identifying cylinder number 1 at its power stroke combustion event. When this sensor begins failing due to accumulated oil contamination, thick sludge deposits, or internal electrical component cracking, the ECU loses that fine resolution reference signal and automatically switches into a degraded operational mode. Sequential fuel injection gets abandoned in favor of less efficient batch injection strategies. Idle quality deteriorates noticeably, and cold start procedures require measurably longer cranking duration. Numerous engines develop mild hesitation characteristics between approximately 2,000 and 3,000 revolutions per minute that mechanics incorrectly attribute to ignition coil failures or fuel injector malfunctions, when in reality, a contaminated camshaft position sensor transmits weakened or distorted electrical signals. A straightforward visual inspection combined with thorough cleaning of the sensor's reading area can dramatically restore smooth operational characteristics. Yet, there exist sensors that receive even less maintenance attention, accumulating contamination simply from normal air circulation past their sensing elements. Number 7. The IAT, Intake Air Temperature Sensor. The intake air temperature sensor usually appears as a diminutive component threaded into the intake manifold casting or integrated directly into the air intake ductwork. It's so inconspicuous and discreet that the overwhelming majority of vehicle operators remain completely unaware of its existence. Its assigned task sounds deceptively straightforward, measuring the temperature of atmospheric air entering the combustion chambers. However, what's genuinely transpiring proves critically important for proper fuel control strategies. Cold atmospheric air exhibits greater density and consequently contains substantially more oxygen molecules per unit volume, whereas hot air demonstrates reduced density characteristics. The engine control unit utilizes this sensor's temperature data to fine-tune precisely how much fuel gets injected during every individual combustion cycle. Over extended operational periods, the sensor accumulates coatings of oil vapor mist, sticky dust particles, or sticky residue substances originating from oiled aftermarket air filter elements. Once contamination layers form, the internal thermistor element can no longer accurately sense the genuine temperature of incoming airflow streams. The predictable outcome manifests as temperature readings that register artificially hotter or colder than actual reality, causing the engine to operate in slightly rich or slightly lean conditions continuously. This situation leads to subtle yet constant power output reduction, accelerated fuel consumption rates, and in certain cases, mild detonation events in extremely hot climate conditions. Automotive technicians routinely discover that careful cleaning procedures using electronics-safe cleaning solutions, while meticulously avoiding physical contact with the sensitive sensing element, successfully restores rapid sensor response characteristics and stabilizes the air-fuel mixture ratio. However, another temperature monitoring sensor exists that controls something exponentially more critical: the temperature of the engine's fundamental core. Number 6. The engine coolant temperature sensor. The coolant temperature sensor ranks among the most influential sensors throughout the entire engine management system architecture. Despite rarely falling under diagnostic suspicion, it communicates to the ECU precisely how cold or hot the actual engine block itself has become, and the computer bases numerous critical operational decisions on this singular input signal. During cold start procedures, the ECU commands enriched fuel mixture ratios, elevates idle speed targets, and modifies ignition timing advance based exclusively on coolant temperature feedback. As the power plant gradually reaches normal operating temperature, those compensatory strategies progressively fade away. When this sensor becomes internally coated with corrosion deposits, mineral scale buildup, or sludge accumulation from deteriorated coolant, it initiates reporting incorrect temperature information. The ECU may falsely believe the engine remains cold when it has actually reached full operating temperature, or conversely believe it's already hot when actually still experiencing cold conditions. The resulting consequences include excessive fuel consumption patterns, rough idle quality, difficult cold start behavior, cooling system fans operating at inappropriate intervals, and long-term engine component wear caused by improper fueling strategies. Numerous engines that superficially appear to suffer from complex drivability maladies achieve complete restoration to perfect operational behavior following nothing more than replacement or thorough cleaning of a malfunctioning coolant temperature sensor. And yet, one additional sensor remains that practically nobody ever services through cleaning procedures, despite quietly causing some of the most financially devastating problems imaginable. Number 5. The VSS, Vehicle Speed Sensor. When the speedometer needle begins exhibiting erratic jumping behavior, the transmission starts making inexplicable shift strategy decisions, or the cruise control system randomly deactivates itself. The silent underlying cause frequently traces back to the vehicle speed sensor. This sensor typically mounts on the transmission housing assembly or differential casing, where it generates electrical pulse signals proportional to the actual rotational velocity of the driven wheels or transmission output shaft assembly. What's genuinely occurring is that each individual electrical pulse gets converted into computational data the ECU employs to determine how rapidly the vehicle travels, when automatic transmission upshift or downshift events should occur, how to manage fuel delivery interruption during deceleration, and when to activate supplementary systems including cruise control and traction management logic. When the sensor accumulates contamination from transmission oil, road grime deposits, metallic debris particles, or sludge buildup, its electrical signal output becomes progressively distorted. Pulses arrive incomplete or demonstrate irregular timing characteristics, and the computer may incorrectly conclude the vehicle travels faster, slower, or even remains completely stationary while actually still rolling forward. In authentic real-world diagnostic situations, automotive technicians frequently discover that simply cleaning the VSS thoroughly, removing metal particles magnetically adhered to its sensing tip, and flushing the electrical connector with contact cleaning solution successfully restores stable signal output and eliminates erratic shifting behavior that numerous drivers mistake for serious transmission mechanical failure requiring expensive rebuilds. Yet an even more critical sensor exists, one that essentially listens to internal engine events like a high-precision acoustic microphone. Number 4. The knock sensor. Bolted directly into the engine block casting exists what fundamentally operates as a specialized microphone that continuously monitors every combustion event occurring inside the cylinder bores. This represents the knock sensor, specifically designed to detect particular vibration frequency signatures caused by abnormal combustion phenomena or detonation events. What's genuinely transpiring is that this piezoelectric sensor element converts mechanical vibration energy into measurable electrical signals that the ECU analyzes in real-time computational processes to determine whether the engine has begun experiencing knock resulting from insufficient octane fuel quality, excessive combustion chamber temperatures, or overly aggressive ignition timing advance. When knock gets detected through vibration analysis, the ECU reacts within mere milliseconds, commanding ignition timing retardation and slightly enriching the fuel mixture to protect engine components from detonation damage. The complications begin developing when the sensor accumulates surface coatings of dirt contamination, corrosion deposits, baked-on oil residue, or gets installed using incorrect mounting torque specifications. Its vibration sensitivity diminishes substantially, and it no longer accurately transmits those critically important vibration signature patterns. The outcome proves dangerous through two distinct failure modes. Either genuine detonation events proceed undetected and the engine operates dangerously close to catastrophic damage thresholds, or alternatively, false signal detection forces the ECU to continuously retard ignition timing unnecessarily, robbing substantial power output and making the vehicle feel excessively heavy and unresponsive. Simply cleaning the sensor mounting surface area and electrical connector thoroughly, followed by reinstalling the sensor using manufacturer-specified torque values, frequently achieves complete transformation of engines that previously felt worn out or significantly underpowered. However, certain sensors don't actively protect the engine during operation. They merely provide warning alerts when mechanical damage has nearly reached critical levels. Number 3. The oil pressure sensor. The red oil pressure warning illumination on the instrument panel represents one of the most anxiety-inducing alerts any vehicle operator can encounter. Behind that warning indicator typically sits a compact pressure sensor that receives remarkably little maintenance attention until catastrophic failure occurs. This sensor threads into an oil gallery passage machined into the engine block or cylinder head casting, and its fundamental role proves simple yet critically important, detecting when lubricating oil pressure falls below safe operational thresholds. Internally, a flexible diaphragm or pressure-sensitive element physically deforms under hydraulic oil pressure, either opening or closing an electrical circuit or generating a proportional analog signal in more technologically advanced monitoring systems. Over extended operational periods, the sensor's inlet passages progressively become obstructed with sludge accumulation, varnish deposits from thermally degraded oil, or debris particles, forming a flow restriction that prevents actual oil pressure from reaching the sensing element effectively. In this compromised situation, the engine may operate with dangerously inadequate oil pressure while the sensor erroneously reports normal pressure readings to the instrument cluster, or conversely, triggering false warning alerts due to sluggish and erratic sensor response characteristics. Repair facilities have extensively documented engines displaying apparently perfect pressure readings on the dashboard gauge, while simultaneously an external mechanical pressure gauge reveals critically insufficient pressure values. That's precisely why cleaning or replacing this sensor during major scheduled service intervals can literally mean the difference between a properly protected engine and one progressing inexorably toward catastrophic mechanical failure requiring complete replacement. Yet another seemingly innocuous dashboard gauge exists that provides false information more frequently than most vehicle owners realize. Number 2. The fuel level sensor. The fuel quantity gauge appears as a relatively minor detail until the unexpected day your vehicle experiences fuel starvation on the interstate highway, while the dashboard indicator still displays a quarter tank remaining. Behind that misleading needle movement sits the fuel level sending unit, a sensor that exists completely submerged inside the fuel tank and receives virtually no cleaning or inspection attention throughout the entire operational lifespan of the vehicle. This measurement system employs a mechanical float element attached to a pivoting arm that slides progressively across a variable resistor element, altering electrical resistance values as fuel level rises and falls with consumption and refueling. What's genuinely transpiring is that the instrument cluster or engine control unit converts that varying resistance into the fuel level reading displayed for the operator. Over multiple years of operation, the resistive contact surfaces oxidize and corrode. Varnish deposits from low-quality fuel formulations accumulate on surfaces, and dirt contamination creates false dead spot regions. The predictable consequences manifest as fuel gauges that bounce erratically, become stuck indicating half tank regardless of actual fuel quantity, or respond with extreme sluggishness following refueling events. In specialized automotive repair facilities, these fuel-sending modules get removed from the tank. The resistive track surfaces and electrical contacts receive careful cleaning with appropriate cleaning solutions, and float mechanism movement gets verified for smooth, unrestricted operation throughout its full range. Numerous customer complaints regarding excessive fuel consumption actually originate from deceptive fuel level sensor readings rather than genuine mechanical efficiency problems. However, none of these individual sensors matter whatsoever if the nervous system infrastructure connecting them suffers from failure. Number 1. Sensor connectors and wiring harness infrastructure. In countless complex diagnostic scenarios, vehicle owners invest hundreds or even thousands of dollars replacing sensors that superficially appear defective, when the genuine underlying culprit isn't the sensor component whatsoever, but rather the electrical connectors and wiring harness infrastructure supplying power and signal pathways to it. Every single sensor depends absolutely on 3 fundamental requirements: correct voltage power supply, solid electrical ground connection, and a clean, uninterrupted signal transmission path returning to the engine control unit. What's genuinely transpiring in millions of aging vehicles operating across the United States involves mechanical vibration, moisture intrusion, extreme engine compartment heat exposure, and minor collision impacts slowly degrading wiring insulation, connector pins, and terminal contacts. Green copper corrosion progressively forms inside connector housings. Intermittent electrical contact develops at connection points. Wire conductors fracture internally while insulation appears superficially intact, and ground connection points loosen and intermittently reconnect with every encountered road surface irregularity. Diagnostic scan tools display fault codes specifically pointing toward temperature sensors, oxygen sensors, position sensors, or pressure sensors as the apparent failed components. Yet, in the repair shop environment, experienced technicians observe that simply manipulating the wiring harness causes the problem to intermittently appear and disappear in repeatable patterns. What the overwhelming majority of vehicle operators never witness firsthand is that thoroughly cleaning electrical connectors using dielectric-safe cleaning solutions, correcting compromised ground point connections, repairing inadequate wire splice joints, and properly securing the entire wiring harness using appropriate fasteners can completely eliminate electronic ghost failures that otherwise prove impossible to diagnose consistently. That's precisely why seasoned automotive technicians invariably inspect wiring infrastructure and connector integrity before condemning an expensive sensor component for replacement. Because extraordinarily often, the genuine problem doesn't originate from the sensor component itself, but rather from the electrical pathway infrastructure responsible for carrying its information to the control computer for processing. The electrical connections represent the foundation upon which every sensor system depends, and when that foundation crumbles through corrosion and wear, even perfect sensors become completely useless. If you found this information valuable and want to learn more professional automotive tips that can save you serious money on repairs, don't forget to subscribe to the channel. Share this video with anyone who owns a vehicle. This knowledge could save them from unnecessary expenses. Thanks for watching, and we'll see you in the next one.